All right. Well, let's get started. Hold on. Hold on. I'm going to remember it this time. Sign-in sheet. There we go. Sign-in sheet. These are steel. Okay. So, sign-in sheets going around. I don't really have a lot of announcements because I think everybody knows the deal. All right, homework 4. Maybe we ought to spend some time talking about that because that is due on Monday. So does anybody have any questions on? Has everybody started it? Yeah, hold on. Yes, sir.
For 4.2, can we just draw like the shear and bending moment diagrams to get
4.2. You mean 4?
4.12, sorry. 4.2.
Yeah, that's fine. That's fine.
Or is it a combination of what's in the RC packet?
Both of the answers are the answers to both those questions are yes. Let me say this, all right, so that everybody's clear. I want everybody to listen up to this, okay? On the problems on the homework assignment, there are a mixture of point loads and distributed loads, okay? If you've got the notion, well, I'm going to take those point loads and convert them into distributed loads, that is wrong, wrong, wrong. You can do the math and you can see that if you look at a beam that has a point load on it versus a distributed load, even if they're ultimately the same magnitude, the moments will be way off, okay? So you have got to go through and grunt through your moments, okay? And you can do that one of two ways. You can draw the moment diagram, which is absolutely fine. Just take all your live loads and multiply the loads by 1.6 and take all your dead loads and multiply them by 1.2 and just draw the moment diagram. There's nothing wrong with that. You can also do the same thing with the equations. Multiply your dead loads times 1.2, your live loads times 1.6, and use the equations, okay? Just make sure that you're computing moments at the same spot. But yeah, that's absolutely fine. Now, for the second problem is a cantilevered problem. It is not a simply supported problem. So your moments are not WL squared over 8. WL squared over 8 is for a simply supported beam, okay? That's what that packet's for. But again, even if you don't understand that packet, it doesn't matter because you've got structural analysis to fall back on. Just draw the shear diagram, draw the moment diagram. So to answer your question, both are fine. Do what you're comfortable with. The only thing I'll say to close is on problem 1, you have to guess a unit weight at the beginning or make some assumptions on the beam dimension, and then those assumptions are going to change. So the point is you're going to calculate moments at the beginning, and then you're going to calculate them again, okay? So if you want to draw a moment diagram, that's fine, but you'll have to draw 2 of them. If you want to use the equations, that's fine, but you'll have to compute 2 sets of them. All right, does that make sense to everybody else? Okay, yes.
So, for our test Friday, will we be able to use that moment packet?
Short answer, yes. Long answer, I'll include the ones you need. So, sound good? All right. So you all are almost finished with the homework, right?
Some professor said that there was a big steel exam on Friday, so
He's a jerk, isn't he? Does it even begin? But I can understand that. But is everybody? No, I can understand waiting a little bit to really dig into it because you got the steel exam. That I can understand. Yeah, and I'm a jerk too, I guess. Now that the visitors aren't here, I can just sort of, I can go back into my jerk mode, right? Yeah. The recording doesn't catch everything. It doesn't catch the video, only the audio. That's only if I hit upload. If I don't hit upload, it just goes away. So. All right, I'll give you that one. All right. All right, that was a good one. Okay. let me go back. If there's no other big questions on the homework, in all seriousness, are there any significant questions on the homework? Okay. All right. Yes, sir.
Will you be accepting emails over the weekend for all of us that put it off till Friday?
Will I be accepting emails over the weekend? Well, when you send any, I don't have this like switch on my inbox that as soon as you send the email, it just, this hand jumps out of the screen and hits no. I don't have that. But look, let me say this. I'm aware, okay, and I'll do my best to respond. But if you send me some email at 2 o'clock in the morning on Sunday, I'm just going to be frank, I'm not responding to it. So I will be asleep. So I'll do my best to answer emails on Saturday and Sunday and whatnot, but not at 2 o'clock in the morning on Sunday night. Like, I'm not doing that. All right? Is that fair? All right. What? I thought that's fair.
Yeah. What if we text you?
Do you do FaceTime?
Android.
Do you have a MySpace?
I do not have a MySpace account. I do not. I do not have a Snapchat account. All right. Back to concrete design. Come on now. All right. So last thing we were talking about was we were getting into the discussion of T-beams. All right. Settle down. Look, in all seriousness, I know that, exam 2 is coming up and you've got the exam in steel. I recognize that. But this is where I think concrete design starts to get kind of fun and really challenging at the same time. So I really want everybody to make sure that they're understanding what's going on. Because if you had issues with, let me put it like this. If you have issues with some of the conceptual stuff regarding beams, things like 0.85 FC prime and how we're calculating A and deriving A, I think that some of this stuff that we're doing now will really help clarify the stuff that you're not only working on now, but the stuff that you'll be examined on next week. So this is some pretty valuable stuff. To refresh everybody's recollection, we're talking about T-beams. So what I mean by that is we're talking about a section where we're counting on a portion of the slab being effective in resisting the loads that the beam sees. So we say we've got the beam, we'll count a portion of that slab as well. It's not the tributary width, because the farther you get out away from that beam, those stresses start to decrease a little bit. So we can't really count on the tributary width. It's sort of an empirical relationship that we use. For T-beams, the way that we compute that effective flange width, if you will, is we have the minimum of 3 quantities. For T-beams, it's the minimum of the length over 4, the web width plus 16 times the flange thickness, or the spacing. So B sub W is the width of the web, or the width of that stem portion on the bottom of the T. And H sub F, that is the height of the flange, the thickness of the slab portion of the beam. And lastly, the girder spacing. Now that's for T-beams. For L-beams, L-beams are just the ones that are on the end. It's either L over 12, BW plus 6HF, or the spacing as well. Okay, now this is the one that I really want to emphasize understanding of, is the added complication of whether or not we're dealing with a rectangular T-beam or a true T-beam. Now I'm not saying that the beam is not T-shaped. I mean, they both look like T's. What I'm talking about is the stress block. Is the stress block a rectangular stress block, or is it a T-shaped stress block? Computing the moment of a true T-beam, one that is a T-shaped stress block, is a little more involved, okay? So we're going to take each of these one at a time and make sure that we understand. So I want to start off with this example. So I want to compute the design flexural capacity, the Fmn, of the following example. So we have a T-beam. Now we've got a flange thickness of 4 inches, okay, and we have a depth, a D value, an effective depth of D is 24 inches. Now we've got 6 number 9s, so we know the area. That's pretty simple. It's 6 square inches. We know the web width is 10 inches, and we've got some some other parameters. So we've got that the beam has the following properties. It's 30 foot long. And then I put that the clear distance between webs is 50 inches, okay? Because I really want you to have an understanding of what we're looking at, because I've got this T section drawn here, but really what I'm trying to represent is an entire composite floor system. So I really want that to make sense. All right. Sound good? All right. Here we go. All right. So okay. So let's see. Okay. Now, I want to take a moment and actually look at what the floor system actually looks like. So let's look at the floor system. Now, this is going to test my my 3D art skills a little bit, but I think we'll be all right. Okay. So bear with me. I'm going to draw something maybe kind of big all in here. So if you are taking notes, just so you understand what I'm doing. Okay. So what I've got is I got something about like this, and I got something about like this. Something about like that. Okay. And this floor system is going on like in isometrics, going on like this. So okay. So I'll erase that because I'm gonna need to put something in there real quick. Okay. So let's add a couple dimensions. So we know, for instance, we know that this dimension right here, that is the web width, and that is 10 inches. Everybody okay with that? Okay. Now, this dimension right here, I'm curious, can anybody tell me what that dimension is right there? 50 inches. Because look at what the problem states. That is a clear distance between inside of web and inside of web. So if I actually took a tape measure, 50 inches would be that measurement. Okay? Now, so real quick, I'm just curious, what is the girder spacing? In other words, from center of girder to center of girder, what's the girder spacing? 60. So the way that I do that, I'll say S, but I have a hard time distinguishing my S's and my 5s, so I like to put little serifs on my S's. Something like that. Okay. Sound good? Now, imagine that this floor beam is going on forever. So the idea is we're going to isolate a particular beam. So what I'm doing is this, bless you. So I have isolated a particular beam right here. So if you want, I can sort of carry this out like that. Ooh. Do that. Do that. So really what I'm trying to do is I'm trying to say, all right, this little T shape that's in a particular range of the floor system, that is the T-beam that I want to analyze. Now one of the problems is that I need to know what this dimension is right here. Okay, and I don't know that right off the bat. Okay, this dimension is the effective flange width. Now, it could be 60 inches. It could be the girder spacing, but it might not be. Okay? We have to keep in mind that when we're computing an effective flange width, it's not the same thing as if we're discussing loads. With loads, we're trying to ask how much is that beam responsible for. With effective flange width, we're trying to determine how much of that slab can we count on for strength. It might be 60 inches, it might be less than that. We're not sure, so we have to go through and do our diligence to compute that. And there's an empirical expression that we can use in the spec. Okay, now a few other dimensions. So each beam we have a rebar. We got 1, 2, 3, 4, 5, 6. Okay, so actually I did that backwards. Okay, so one thing, we know that this dimension right here is h sub f, and that is 4 inches. And this dimension right here is d, and that is 24 inches. Was that right? Okay. Now, I'm not, let me be clear, I'm not being loose, fast and loose with this notation. I'm being very diligent. When I say h sub f, that is what we will call the flange thickness in this course. Okay, so when I say h sub f, that's what I'm talking about. When I say, when I use the term b sub w, I'm talking about the width of that stem, the width of the web. Okay, so we have to, make sure we're being diligent on that. All right, sound good? Yes. No. The beams are, no, that's a good question. The beams are physically spaced 60 inches apart. I'm not changing that. I'm just asking how much of that slab can I count on? It might be 60, it might not. It's a computed value. So does that sort of answer your question? What's it symmetrical? I don't understand. No. What I'm saying is I could have a B that's 54 or 52. Again, it's a computed value. I don't understand what you mean by symmetry, though. I will admit I'm a little confused there. Are you saying if the beams were spaced differently?
Yeah.
Well, if you did that, then essentially what you'd have to do is compute however much effective flange width you have over here and how much effective flange width you have over there, and then add them up. But let me be clear, that's more often than not something we don't want to do. That's just going to create complications. And also, it's usually pretty avoidable. Okay, we're talking about beam spacing. All the architect cares about is that we've got enough space up here for the floor system. I don't know that the architect really cares what's going on between the drop ceiling and the next floor above. So why would we as the engineer make it complicated by, having a beam here, and then a beam all the way over here? Do you see what I mean? No, does that make sense? I mean, would you make it complicated? I'm asking you. Do you see what I mean? Does everybody else, do you have any, is this making sense? I mean, my point is, if you've got a floor system, why would you do this? Like, if here's the floor, why would you put, a beam here, and then a beam all the way over here? Like, why would you do that? Do you see what I mean? If it was me, I would just, make it even. Do you see what I mean? I mean, this is important, so I really want this to make sense. Everybody all right with this? All right. Okay. Let's go through and actually compute B. All right. Now we're talking about a T-beam. Okay. So to compute that, we take the minimum of B sub W plus, I'm doing this one in the middle, 16 HF. We have L over 4. And we have S. All right. Does everybody see where I'm getting that? All right. Does everybody see it in the notes? Now, that's for T-beams. L-beams are the ones that are on the ends. Okay. So if we were on the end, we would use that one. All right. Sound good? All right. So, all right. Let's use a little bit of common sense here on something. So how long is the beam? Anybody see any issues with that right off the bat? It's in feet. So terrible. So it needs to be in inches. So I have 30 feet times 12 inches per foot divided by 4. Okay. Middle one, what is B sub W? Huh? 10? and plus 16 times what? And what's S? All right. So the minimum of what? What's the top value? 90. What's the bottom or the middle one? 74 and then 60. So in this instance, it was 60. It could have easily been one of the others. Okay, so to I guess more clearly or to more generally respond to your question, what I would say is this. Compute the effective flange width, counting on this girder spacing, compute it for this one and take the average, okay? But again, it goes back to my original point. I mean, think about a bridge, If this was a bridge, you'd space your beams evenly. You wouldn't take one beam and space it at 3 feet and then the other space it at 10 feet. Do you see what I mean? I mean, there are some instances where maybe you need to do that, but more often than not, you're going to keep it simple. All right. Sound good? All right. So is everybody okay with this? Okay. Now, this is where the important stuff really starts to come into play, okay? So this is how we're going to go about this. So let's be clear for our beam, the effective flange width, if you will, we have, this is 60 inches because we went and computed that. So if you want, you could say this right here, that's our beam. Does that make sense? All right. Now, let's keep this simple. All right. When we compute moment capacity, M sub n, okay, remember we compute it by saying it's a force times a distance, right? Force times the moment arm. Bless you. Okay. Now, let's talk about the force. Okay. We said we have a force in compression and a force in tension. So the first thing that we ever did when we computed moment capacity is we recognized what truth about C and T? They had to be equal to one another. Okay, so let's just start there. Let's just keep it simple. Okay, so what we're doing right now is we are determining the location, okay, of the neutral axis. Okay, now just so you're clear, if I write NA, that's what I mean. And we are determining that based off the relationship that C equals T. Okay? All right. Sound good? So let's start off with T. How do I determine the tensile force in that beam? Just help me out.
P sub S times Fy times B minus A over 2.
No. Okay, you're talking about the, first off, you're talking about the moment capacity because you're saying ASFY is the force and D minus A over 2 is the moment arm. That's a moment, okay? What I'm talking, there you go, exactly. So the tensile force, the T, is the area of steel times the yield stress. Is everybody okay on that? So ASFY will give us however much tension there is in the beam. So we'll put that over here. All right? So we'll say ASFY. Sound good? Now, how do we determine the compressive force? Not the moment, compressive force. How do we determine that? How did we do it before? Okay, we had... There you go. There you go. It said 0.85 FC prime AB. Does everybody remember that? Now, here's the problem. We said 0.85 FC prime AB. What was AB? AB was the area of that stress block, right? Now, AB assumed the beam was a rectangle. It's not a rectangle anymore, right? Okay, so this is how I'm going to approach this. I'm going to say it's the stress 0.85 FC prime times the area in compression. Okay? In other words, what I'm going to try and do is figure out how much of that concrete beam needs to be in compression in order to meet C equals T. Everybody okay with that? So let's just keep this simple, okay? So I propose then that the area in compression is ASFY divided by 0.85 FC prime. So let's just keep it simple. Let's just plug and check. So what's AS? There we go. What is FY? There we go. And 0.85 times what? What do we got? 105.88. Do I got a second on that? I don't have any seconds. There we go. Yeah, sure. No. We got to have a second. 105.88 square inches. Sound good? All right, now, I propose that in order for compression to equal tension, I must have a compressive stress block that has an area of 105.88 square inches. Everybody okay with that? Okay, now, let's look at the beam, okay, and let's see what's going on. All right, so, has everybody got this? All right, so, let's just keep this simple. All right, so here's the beam that we're analyzing. Okay, now, what's this dimension right there? HF, which is 4 inches, right? Sound good? What is this dimension right here? First off, what's it called? No, if we're talking about just the beam, we're talking about B. Now, it just so happens to equal S in this example. It might not have equaled S. It could have equaled BW plus 16HF. You see what I mean? That's why I'm calling it B. I see where you're getting at, but I want to be diligent on my notation. And this was what? 60. Okay. All right, so let's be clear on something. What is the area of the flange? Just keep it simple. What's the area of the flange? There you go, BHF. Yep, which is 60 inches times 4 inches, which is 240 square inches, right? Now, the area that is required to be in compression is about 105.88 square inches. So let me ask you this. That region that's in compression, can I completely contain it in the flange, or does it need to dip down into the webbing? It's going to be completely in the flange. In fact, it's probably going to be something about like this, right? Like my region in compression is probably going to be something like that. Something like that, right? Yeah, it's really easy to compute, right? Now, but here's my point, okay? That stress region, see how it's rectangular in nature? Like it's a big rectangle. I propose that because of this comparison right here, we have what's called a rectangular T-beam. Yep, exactly right. That is important. I really want that to make sense.
So it's only if the area of compression equals the area of the flange or
Less than, yeah. If it's greater than, then we have a true T-beam, because then the T shape, or the stress block's got to dip down into the web a little bit, and we have a true T-beam. That's a good point.
that assumption really valid if it's less than or equal.
Yes, exactly right. Yes.
If you put loads on that, would the area of compression change?
No. We're talking about ultimate capacity. We're talking about what the beam can supply, okay? And the beam, the ultimate capacity of the beam, that's a good point, but let's be clear. The ultimate capacity of the beam has nothing to do with the loads. It has to do with C equals T, okay? That isn't affected by the loads that are on it, okay? It's a good point to make, but it doesn't affect this, all right? Everybody okay with this? All right. Now, Mr. Fig, you already had the stress block depth calculated, but what I want to really emphasize is this. Because this is a rectangular T-beam, keyword rectangular, I can do this. I can literally use the same equations that I used before. That's the important point I want to make, because those equations that we did before, bless you, I mean, how did we write them? We assumed we had a tensile force in the steel and a rectangular stress block. It's the same story, okay? The big thing is just making sure you're referencing the right values. Your ASFY over 0.85 FC prime B, B is your 60 inches, not your 10 inches, because that's the width of the stress block, okay? That's why I'm being very careful with that notation. So it's 6 square inches, 60 KSI, 0.85 FC, or FC prime, which is 4 KSI. And then this is 60 inches. And what did you get, Mr. Fadiga? 1.76, 5, something like that. Yeah. Okay, and now what you did is you said, well, here, let's just take this and divide it by 60. And that's exactly right. Nothing wrong with that at all. The big thing that I want to emphasize, though, is that you can go back to just using the same equations that we did before. So, and I'm going to chug through this because you're going to need to do this on your homework, so I want to make sure everybody's comfortable with it. So, AS is 6.00 square inches, 60 KSI. We've got, what's D? 24 inches minus 1.765 inches over 2. Now, I'm going to go ahead and do this right now. When I compute this moment capacity, it's going to be in what? Inch kips. So to convert that, go ahead, multiply or divide? Divide by 12, because it's 1 feet per 12 inches. So let's go ahead and do that and tell me what you get. What's that? That's where this is right here. I went ahead and just tacked it on the end. Excuse me. We got an answer?
693.525.
So we'll say 693.5. Do I have a second on that? There we go. Now, is that the design capacity? Exactly right. I did not do phi. So now you tell me. I'm not going to tell you. You tell me. What do we need for phi? What's the step-by-step? It's tension or compression controlled. And now to make the determination of whether or not it's tension or compression controlled, we need what? What value do we need to compute? The strain in the steel. We need the strain in the tension region. So to compute the strain in the tension region, what dimension do we need? Similar triangles. And what are we missing? C. We need that neutral axis depth. So you tell me, how do we compute C?
A divided by 0.85.
Well, divided by beta 1. It happens to be 0.85, but let's be clear that we're not confusing that. So C is A divided by beta 1, which is 1.765 inches divided by, and then beta 1 happens to be 0.85 because we're dealing with 4 KSI concrete. But beta 1 and this are not the same thing. This is always a constant 0.85. Beta 1 could change, okay? They just happen to be the same quantity. So what do we got here? 2.076. All right. Now that we've got C, now what do we compute? Epsilon sub t, our strain in the steel. So our strain in the steel is what? Now, somebody said the term similar triangles. They're exactly right. So epsilon sub t is what?
0.003 times quantity B minus C over C.
There we go. Remember that? All right, so 0.003, then we have something minus 2.076, which is, what's that something? There we go. So what do we get? First off, what are the units going to be? Let's see if everybody's paying attention. There are no units. This is a strain. Remember, strain is inches per inch or millimeters per millimeters. There's no units. So now what do we got here? 0.03168. Do I have a second on that? So that is actually a crazy amount of strain, right? Or is it? What does it have to be greater than for our phi to be 0.9? Well, no, 0.004 is just the minimum ACI requirement. For phi, it's 0.005. But I'm just making sure you all keep track of your decimal places. It's greater than 0.005. That's a crazy amount of strain. That's exactly what we like. So that means that phi is 0.9, right? Sound good? So because of that, I'll sort of underline that. Phi mn is going to be 0.9 times 693.5. What does that come out to be? $624.15, so we'll say 624.2. Do I have a second on that? That's not so bad, right? But the key thing to determine, the key thing to keep in the back of your head is this was easy because we were dealing with a rectangular T-beam. Okay? We were dealing with a scenario where the stress block was in fact rectangular. Okay? Do you have a question? Oh. Anybody else? Is this good stuff? Anybody got any questions? All right. So because I'm devious and I'm a crafty guy, why don't you take a wild guess what you think's going to happen here on 9B? It's going to be a true T-beam. Well, we'll check that and we'll see. Now, what I've done for this T-beam is a little different. So, number one, let's see. So, same material properties, and really all I did was change up the dimensions a little bit. So, first off, instead of us having to compute an effective flange width like we did on the last one, I'm just giving it to you. So we'll say that the B is 30 inches. All right? It's a 4-inch flange thickness. It's a 14-inch wide web. The depth is 30 inches, and we have 8 number 10s. So instead of making you look up the area, we'll just say, I'll give it to you. We'll say it's 10.12 square inches. Okay? Sound good? So in this instance, let's see if the rectangular T-beam instance is going to work. So the big thing is we are going to apply the same theory that we did before. Okay, the same theory. Sound good? All right. Again, I think this is really important. I know that right now everybody's thinking about their homework and the celebration in steel, but this, I think, will really help reinforce what you're doing on this homework right now. Reinforce. Actually, no, I wasn't, but I'm going to take it. I'll give myself like a 7.5 out of 10 rating on that one.
That's high. 7.5? Yeah.
Being very generous.
I could have given myself an A. I gave myself an average C, so What? Oh, wow. Wow. You're probably like, man, I wish there was a visitor here so I could just, hammer him over the head with that. Talk correctly. Yeah, that's right. That's right. All right, okay. So what I'm going to do for this one is I'm going to draw out the dimensions as they were reported and make sure everybody's clear on what's going on. So we have this dimension was given to us as 30 inches. This dimension here was given to us, and you tell me, what was it? There we go. This dimension here, again, not the total depth, just the effective depth to the rebar is, what is 30? All right, and again, I'm saying D equals 30 inches. I'm using the notation, which, by the way, is the exact same notation they use on the FE exam. So if that helps out or clarifies some things. So 8 number 10s. Okay. All right. This is 14 inches. And then what else do we have? We have FC prime and FY. Sound good? Making fun of my review sessions? My goodness. Now that one was a 5.2 out of 10 right there. All right. Okay, we're going to handle this one the same way we did the last one. Okay, so let's be clear. What was the first thing we did? The area that was in compression. And how did we do that? Like what principle? C equals T, equilibrium. That's where we start. Okay, so we'll say equilibrium. Exactly, yeah, I just gave it to you. Because if you can do it once, you can do it again. Literally the same thing. So, all right, so this is what we did. We said 0.85 FC prime, area in compression equals ASFY, okay? That make sense? And then we say, all right, let's solve for the area in compression required to achieve equilibrium. So we have area of compression equals ASFY 0.85 FC prime. So that is 10.12 square inches, 60 KSI. And that. Now what do we get? $178.6. Do I have a second on that? Yep. All right. So we'll say 178, and I got, what was it, 0.59? We'll do 2 decimal places. Okay, now, so that is how much area we need for our stress block in order to achieve equilibrium, in order to meet C equals T. Now, how much area is our flange providing? 120, because the area of the flange is BHF, which is 120 square inches. Sound good? So I can do better than that. That's a sloppy. Okay. Does that make sense? Okay, so in this instance, it's the flip side. We don't have enough area in our flange to provide all of the required compressive stress. So in this case, we're dealing with what's called a true T-beam. In other words, if I look at the stress block more than likely looks something about like this, right? Make sense? So in this instance, we are dealing with a true T-beam. Okay, so what I'm really interested in is that you all have the ability to distinguish between what is a rectangular T-beam and what is a true T-beam. Does that make sense? Okay. Now what we're going to do is we're going to look at this stress block and we're going to see how can we determine the depth of our stress block, and then we're going to call it. Okay. So is everybody okay with this so far? Okay. All right. So you would agree then that the neutral axis is somewhere in the web. Do you agree with that? So help me out. Let's take a look at this. Let's try and let's see if we can derive some formulas. All right. So here's a T-beam. And the stress block looks something about like that. Is that a fair statement? Now, let's put some dimensions on here. So this dimension is h sub f. This dimension right here, was that b? That one up top? All right. We've got this dimension right here, which is h sub f, right? I would propose h, there we go. That, well, we're talking more number 2. That's a all right. What I'm interested in is determining A. Now, let me be clear. I'm still measuring A from the same spot that I always measured it before. A is from the top of the beam to the bottom of where that stress block is. That was the same definition that we had when we did just regular old singly reinforced rectangular beams. All right? Sound good? Now, let's just look at this and let's see if we can write a formula for the area of that stress block. Now, what I'm going to do is I'm going to split it up into 2 instances. Okay? So I propose that the area in compression over here is as follows. It's the area of whatever's going on top plus whatever's going on the bottom. So the area of this right here, what is that? BHF, which is the area of the flange. We've already computed that, right? So I propose it's the area of the flange, okay? Plus, now that rectangle down below, how wide is it? BW. And how tall is it? A minus HF. So I propose this as BW. A minus H sub F. And what don't we know in this expression? A. So all I've got to do is take that expression, rearrange it a little bit, and solve for A. So what do? Take the flange, move it on over to the left. So A compression minus A flange. Okay, and that equals this quantity over here. If I divide by BW, that gives me A minus HF. So I propose that A equals the area in compression minus the area in the flange divided by BW plus HF. Not too bad, right? Simple. Okay? So let's plug and chug and then we'll call it. All right, so we have 178.59 square inches minus the area of the flange, which is 120, divided by B sub W, which is 14 inches, plus what? So what do we get? Say it again. 8.21. I got a second on that? See, I got 8.185 or something. You have a decimal value off or something? Okay. Everybody okay with this? So that's how deep that stress block needs to be for this beam such that C equals T. Now, we haven't found our moment expression yet. That comes next time, okay? But the idea is that now we know how deep this stress block is. We know what the tensile force is. We know what the steel force is, or the compressive force is. I'm telling you, force times distance, it's the same thing. The only difference is it's a little more involved, a little more intricate. Sound good? All right. That's all I got. I will see you all next time.